Alright, so this is Christian. We're doing this one backwards here, so I'm going to start at 10 and then we'll work our way up. But for the first question, basically we have two rotating frames here, and I'm asked to find the acceleration of point P. Of course, I'm given the omegas and the theta here, as well as the radius. So the way I started this one off is just by looking at, the position is the position, the derivative of that is cross product of the radius and omega, and then of course, we get the acceleration here as well. So this is kind of the guide that I followed here. I'm just starting off with what I can figure out. Omega cross r gives me this. Omega cross r, which is just omega cross the solutions that I got here, gives me this solution here. I was thrown off with how to find alpha. I still don't really understand why I want to do it this way. If we look at the picture here, I mean, obviously, as this thing rotates this direction, the axis of rotation in this case, it's K, that's going to start to come down, and eventually it's going to be in alignment with Y, which is why we get the J direction here. I'm just not sure why it's negative 20 instead of just negative 5. So that isn't very intuitive to me. It's something I've got to figure out. But once I got that from the solution sheet, I was able to just do the cross product again and then add it all up, and I get this as my final solution. Question 9 was trickier in my opinion, but basically we have rod AP given its omega as well as its alpha, and I'm asked to find the omega and alpha of rod BD. It's important to note that rod BD has a collar around it that's allowed to move freely along its path. One of the first things I do is start off by drawing a triangle because I realize I'm going to need to figure out the lengths of the other sides. It's able to be accomplished by taking the ratio of the length opposing the angle and putting that in sine to be able to solve for the length of BP as well as AP. Velocity is omega r, with r being AP in this case, and that velocity is going to be at a 90-degree angle to r, which gives me this 25 degrees. I know that all of this tangential velocity is going to be converted into velocity of BP, which gives me this omega r. Right now I'm just looking at the tangential velocity of BP, which is why I need to use the sine 45 to break down the components of the VP vector into two parallel vectors corresponding to both the tangential velocity as well as the relative velocity that's going to be going towards VP. So that's going to cause the collar to slide towards it. Anyways, I'm able to solve for omega pretty quickly. Finding the acceleration is a lot more difficult. Generally speaking, that acceleration is going to have two components. The normal acceleration right here, as well as the tangential acceleration. I'm confused why we have to subtract the normal acceleration. Anyways, we break it up into individual components. I'm able to find 25 degrees here from looking at the drawing that I've made. Then the normal acceleration is obviously going to be at a 90-degree angle from that. So that gives me acceleration of p in the I and j components. Now I need to find the velocity that's going towards b, which is here. I'm calling the color u. And of course that's going to have I and j components as well. This is the full acceleration equation here. I have acceleration of the point as well as its relative acceleration and Coriolis acceleration. On the left-hand equation was the numbers that I was able to find pretty easily and quickly. The relative acceleration is found by doing another cross product similar to what I did here, but this time r is p relative to b, and that gives me these alphas as well as omegas. Need to also consider the change in the acceleration of the color going towards b, and this part right here comes just from what the Coriolis acceleration right here and right here. This is a constant, this is a constant, this is a constant. I'm able to subtract and add this over, and I'm left with this. Do the same thing, the j component, then I can solve simultaneously by multiplying this entire row by 0.342 divided by 0.9396 and subtract everything over. And that leaves me with just an alpha. You can then divide the values over to the constant and solve for alpha. Alright, for question 8, we've got a drum that has a cord wrapped around it. There's an extruded point in the drum that comes out of the screen, makes contact with the surface at point A. Given the velocity and the acceleration of d, I'm asked to find the velocity and acceleration of, or just the acceleration of points A, B, and C. One of the first things I'm going to want to do here is find out what omega is. Velocity is omega r. R in this case is the distance between A and B. And this is similar to a tire just rolling on the ground. Once I have omega, I can use that to find the acceleration of A pretty quickly. There is not going to be any tangential acceleration at this point because it's not going to be slipping, so we're going to just have normal acceleration. Going to just be working with a lot of relative accelerations at this point. So acceleration of A is equivalent to the acceleration of B plus the tangential and normal accelerations of A relative to B. The acceleration of B does have a horizontal component which is given. It's the 30 inches per second squared to the left. No, it's to the left because obviously that's going to be going the same direction as D is being pulled, and it's going to be going at the same rate. I do not know what its acceleration is going to be going upwards though. Okay, the way I want to figure out which direction these are going here for the A relative to B portions, I just visualize if I'm on B moving this direction, what is A going to appear, how is that going to appear to be traveling? In a tangential direction, it's going to be going to the right, and as I'm coming up, the A is going to appear to be coming down. I'm able to break this up into the I and J components. By looking at just the I components together, I can solve for alpha, which is 15 radians per second squares clockwise. I can then find the acceleration of A by looking at the acceleration of G. Same kind of situation here. Now, of course, the acceleration of G is going to just be horizontal because it's the centroid. It's not going to have any vertical acceleration. It's going to be going to the left because if I'm on G looking at A is going to be appearing to go to the left and up, which you can see here. Again, just looking at the I components, I'm able to solve for the acceleration of G. And I can then use that to solve for the acceleration of B, which is 45 to the right. Again, on G, looking at B, it's going to be going to the left. Distance is 5. And it's going to be going up. Then get the I and J components, draw a triangle to figure out theta and the magnitude of the vector. Follow the same process for point C. And there we go. Got the accelerations for point A, B, and C. Alright, and for question 7, we've got rod BC. It's rotating counterclockwise. I'm given the omega and RPMs. Asked to find the accelerations of point A and D. Accelerations are a little bit harder than velocities, but that's okay. You can see point A by looking at the picture. It's on a roller and it's confined to moving in the J direction. I want to convert RPMs to radians per second, which can be done pretty easily by multiplying 2 pi over 60. Then find the velocity of point B. Not sure if it's really going to help me at this point, but it's easy to do, so there we go. Then want to find the acceleration of point B. I tend to just kind of work step by step. B is the closest point that I have of information, so it makes sense for me to do it that way. Acceleration, it's going to be broken down into tangential as well as normal accelerations, which can be found here. Obviously the acceleration of point C is 0, and so I quickly realized that there is not going to be an alpha because it's going to be moving at a constant rate. So I'm left with just 4 omega squared, which equals the 88.27. But I really want to find the acceleration of point A. So I can use then acceleration of B to help me with that. Go ahead and make a triangle to be able to solve for theta. My r in this case is going to be 8, but it's going to be broken down into its tangential and normal components, which is why I want to use the cosine of 30 here for the I components. And we're ignoring the tangential acceleration here. I'm not sure why, or I mean the normal acceleration. I'm not sure why we do that sometimes. We did it in one of the first questions we went over where we minused it instead of adding it. Here we just completely ignore it. And the only thing that I can think of is that the normal acceleration isn't going to have an impact on the acceleration of point A, which I can kind of wrap my head around. So anyways, in the I direction or the X direction here, I just minus this over and then divide by 8 cosine 30, and I'm left with alpha. Can then plug that back in here to find the acceleration of A, and I just go through the same process with D, being careful with my angles just by, looking at the triangle, figuring things out. Need to do another triangle here because I have this acceleration of B, which is known, but I gotta break the 30-degree angle into X and Y components and then add them all up again to find the magnitude and angle for the acceleration of D. Luckily I didn't have to find the magnitude and the angle for the acceleration of point A because it's confined in the J direction. And the questions seem to get easier with time here. So basically we have this setup of gears. The rod AC is going to be rotating counterclockwise. Then at the same time, the gears are going to be rotating as well. This gear B is rotating counterclockwise. I'm asked to find the instantaneous centers of rotations of gears A and C and the angular velocities of gears A and C. So one of the first things I'm going to want to do is start off by making my drawings. I want to find the point which they contact so that I can find the velocity of that point as well as the velocity of point A. Both of these are going to be moving downwards here. The velocity is found by omega r, which gives me this 1.6, and that is based off of the omega for the gears. The omega for the assembly is 4, and that's going to be just a different distance away. It's going to be a different r. I can then use this triangle and the relationship here to determine the omega of the instantaneous centers of rotation, which is the differences in velocity over the difference in x. Again, velocity equals omega r. R in this case is going to be the length from point A. So I just got to divide by the omega. I get 0.3 meters left of A. For the next one here, I just end up following the same process. Obviously the velocities are going to be heading in a different direction. And this time the velocity of where the gears meet is smaller. And so it puts the origin to the left. At first I was thinking it was going to be on the right just because I thought it might be symmetric like that, but yeah, this makes more sense. So again, just draw one line where they start and then connect the tips of the vectors. And then the length L can be wherever you want it. Like I could have had L be this point right here where they contact. Yeah, that would just be harder to specify given the diagram. It's easier to specify it based off C. So again, got omega r here to find the vectors of the velocities, and then the omega of the imaginary center of rotation that we're creating is the difference in velocities over the difference in the x values, or the r between those velocities, get 2. And L is found in the exact same way as before. The L is going to be determined based off of the velocity you pick, and so if I picked 0.8, then it would have been left of where they contact. But since I picked 1.2, L is going to be 0.6 meters left of point C. Alright, for question 5, given the rate at which this wheel is traveling, which is 6 inches per second to the right, I'm told the distance between AD is 5 inches, distance between BE is 4 inches. I'm asked to find the velocity of point E. And in these situations, I want to take into consideration the point of contact here. Okay, so WR, or omega R, or in this case is 6 inches. We're looking at the distance from this point right here to this point, which gives me an omega value of 1 radians per second. To find the velocity of A, I want to look at the distance from this point to this point, which is going to be 6 inches plus the 5 inches. So it gives me a velocity of 11 inches per second to the right. I am then looking at the point of contact here, which I called F in this case, because it comes after E. Velocity at that point is going to be 0. Velocity of B relative to F is going to be the cross product of the omega of B and its R, which is going to be up 6 inches and to the left 5. Do that cross product, get this. I can then do the same thing, but looking at the velocity of A and the velocity of B relative to A. I know the velocity of A because I found it earlier. Just need to do the cross product once more. And R in this case is just looking at A squared plus B squared equals C squared and doing the algebra to get this length in the x direction, and it's going to be going down 5. Compute that cross product, and I'm left with this equation here. Oh, this equation here. I can then set them equal to each other, solve them both simultaneously, following the same process I described earlier. Looks like I had to multiply everything by -4/6 and subtract it to get rid of the omega e, and I can solve for omega AB, and then I can substitute that into one of these two equations to be able to solve for the omega e. Once I have that omega, I can determine the velocity by crossing the omega e with its r, which is just 6 inches above. Again, because we're looking at this point of contact to determine the velocity here. The solution manual has it going the other direction, it has it going to the right. I think that's wrong, it's got to be going to the left, and that's what my math has here. They were messing up with the negative sign, I think. If you just look at it, how the force is going to be applied here, it's going to have a downward vector. It's going to be pushing this end down, so it's going to go counterclockwise, and it's going to push it to the left. There's no way here that this thing is going to overcome that without there being some slip involved, which I don't think there is. And I mean, if this was powered as well, sure. But yeah, with the way it's set up, this E has got to start, it's going to get pulled towards D. Alright, for question 4, D is rotating counterclockwise. It has to find the velocity of A and the velocity of B. A is going to slide here, so it's going to be constrained in the I, or the X direction. I'm able to easily find the velocity of D. I can then use that to help me find part of two equations that I'm going to need to use to be able to solve for the velocity of A and B. So the velocity of A is equal to the velocity of D plus the velocity of A relative to D. Again, just using the cross product here. Getting it in its components. Adding them up. Then I can just solve for the omega of AB by looking at, looks like in this situation I looked at just the J component. Then able to plug that back in to the I component, which is going to be going to the right. To be able to find R for B relative to D, I had to draw this triangle, do a little bit of math to be able to find the length here because it wasn't given. Then just do the same thing. Again, I found the velocity of D right away. Just got to do the cross product here. And then, because D is going to be free to move in both the I and the J directions, I want to find its magnitude and its angle. Alright, for question 7, given just partial information as to the I and J components of the velocity of points A, B, and C, I'm asked to find the angular velocity of the disk, or the omega of O, and the velocity of point B. One thing that kind of put me through a little bit of a loop here is just that these are not drawn the right direction. They seem to just be drawn in an arbitrary fashion. I mean, just take a look at the velocity of A, Y, and the J direction. This thing should be pointing down, right? in the X direction for B should be going to the left. C should be going to the left. So that threw me off a little bit, but that's fine. So start looking at the velocity of the origin compared to the velocity of A. And basically I just got to do a bunch of cross products here. Putting in the value that I'm given. Looking at different points until I get to a point where I can substitute in the velocities that I have for A as well as the velocities of B, which was given, velocity of B over A, which I found out. And then I can just compare the individual J and the I components. I don't find anything here, so I do it again. The velocity of C, and right here I'm able to find the X component of the velocity of A that I can then substitute into this equation to be able to solve for omega. And once I have omega, I'm good to go to just plug it into the equation for the velocity of B. I was already given the X component, so I want to find the Y component, which is 1 meters per second. And there we go. Then for question 2, we've got a powered gear A. It's hooked up to B, and it is going to lift up a load 20 feet. I'm told that A maintains a constant speed of 120 rotations per minute, and it takes 5 seconds to get there. I'm asked to find the number of revolutions that gear A is going to need to make to lift the load 20 feet, and the time required to do so. So I thought this one was pretty easy. I did a little bit of a different route than the solution manual, and hopefully that's okay. So I wanted to figure out how many revolutions B is going to need to take to lift the load 20 feet. I want to convert feet to inches here. And then what I'm looking at is I know I got to go 20 feet, and the circumference of this thing is going to be 2 pi r. 2 r is 30 times pi is that. And so yeah, I'm able to find about 2.5 rotation is all that's going to be necessary. I don't need to compare the circumferences exactly to each other, just the radiuses will work because that 2 pi is going to be a constant. They're just going to cancel each other out. So the 18 over 3 inches gives me 6. That means for this to rotate once, A needs to rotate 6 times. So I just times 6 by the number of rotations required of B to find how many revolutions are going to be required. Then turn revolutions per minute into revolutions per second just by dividing this number by 60. It's 2 revolutions per second. If I divide that then by 5, it's going to take 5 seconds. Take it to 120 RPM or 2 RPS. I find that it's accelerating at 2/5 rotations per second squared. And then use the good old kinematic equation used way back, it seems like now, to be able to find it's going to take 5 revolutions. No, it's going to do 5 revolutions by the time it gets up to speed, which is going to take 5 seconds. Right? We know that it's going to need 15.279, so subtract the 5 revolutions from that, and after 5 seconds it's going to require 10.279 more, Now it's going 2 revolutions per second, so it's going to take 5.14 more seconds after the 5 seconds to give me a total of the 10.14 seconds. Alright, so we got this little belt set up here. 3 different sized positions that the boat can fit into. Obviously this is going to change torque and how fast the axes rotate given the angular acceleration of shaft A. And I'm asked to find how long it is going to take for shaft B to reach 400 RPMs with the boat in each of the 3 positions. So I just broke it up into time 1 times 2 and times 3. Going to want to convert RPMs into radians per second. Ends up being about 41.9 radians per second. Can then look at the relationship here. For every 1/2 rotation of A, B is going to rotate once, which is why I get this 1/2 of omega B is equal to omega A. Tells me omega A needs to be going at just half the rate of what I found B needs to go at, and I'm able to just divide by its acceleration to find how long it's going to take. In its second position, they're going to be equivalent to each other, 3 inches, 3 inches, so I just got to find out how long it's going to take for A to get to the 41.888. And then in its final situation, A needs to be rotating twice as fast as B. Pretty easy. Alright, thank you.